Hey, welcome back to Subspace Mechanics. Today we're going to have a brief discussion of special relativity, which comes out pretty quickly from this analysis. Typically, special relativity is derived from starting point of Maxwell's equations, showing how they're not invariant under Galilean transform, and showing how the Lorentz boost factor preserves the electromagnetic wave equation under transforms, and then from there you can derive the rest of relativity, as Einstein showed, of course. In our case, we're going to try to go back to our subspace assumption, where we have some distribution of gyrons in a phase space of some sort, and show how this produces a similar result. In fact, we'll take a very simple theory of the phase space. We're going to ignore the spin of the gyrons. We're going to say that, assume that these gyrons, this is our subspace particles that we use to build our space, are just a function of a velocity parameter, and that somehow through either a collision mechanism or other type of random process, the randomization occurs of these gyrons and they become a Maxwellian distribution, acting kind of like a gas. So we have some normalization of density, and in the Maxwellian distribution we have a factor of 3/2. And our velocity, and we have a standard deviation. This is a speed now, a velocity in our subspace coordinates, which represents the average peculiar velocity. In other words, the average motion different from zero. So we assume we're at rest here. This is at rest in subspace. And of course, you probably know, due to gauge invariance, that there's no way to actually measure if we're at rest in subspace. So I'm going to put this in quotes, but this is an assumption. Typically subspace velocity is associated with magnetic vector potential, and as we know from family of experiments beginning with Michelson and Morley, our measuring devices transform themselves to make this difficult to measure. And but nonetheless we proceed, and we are assuming that our gas, that our the sigma parameter, the average peculiar velocity, is actually the speed of light, and in our rest frame. So then we go on to shift. Suppose we're moving through this subspace at some speed, let's call it u. So then we have a new distribution. Now, I should point out that some of the relevant integrals here, of course, the point of this sigma is that if you take a integral over all velocity space of v squared times f of v, we get sigma squared. This is how we set it up. This is the average peculiar velocity. And this is the original unshifted. But if we call this the prime, the shifted distribution function, we actually get a different result. And that is that we have the shift comes out in the average peculiar velocity, the square of it in this case. It needs to be squared because if it was not squared, then we'd have negative and positive, and the integral would be 0. So we're interested in the square. And you can see why this is true in one dimension. If you consider the one-dimensional integral, x squared e to the minus x minus a squared over sigma squared dx. And this is, remember 2, and we have our famous square root of pi, and this becomes 2a squared plus sigma squared. We haven't exactly removed the factor of 2 here with this simple example trying to remove the constants, but you can see that we wind up with a similar structure in one dimension. And we should point out here that what sets our metric is this parameter that we're actually calculating here. This sets our metric, the average motion of the gyrons. That's what sets our speed of light. So in one frame we have this as our speed of light, and in another frame we have this coming out as our speed of light. And of course, if we want to transform from one to the other, we're going to call this, let's call it c squared, and we'll call this c prime squared. And so if we want to shift from one frame to another, we need to multiply by a boost factor here, which is going to be our c over our c prime. So it's going to be sigma over square root of sigma squared 2 squared. This actually should be a minus sign here. Just a question of how we define this parameter. Indeed, it's because what we're looking for is, my apologies. If we look at this formula right here, and we solve for the sigma squared, it's and on the top one we had sigma squared being c squared. So our Lorentz factor, which is going to be our sigma prime over sigma, or sigma over sigma prime, and as I've written it here, is going to be, I missed my sign again here, c squared over, c over the square root of c squared minus u squared. which is, of course, 1 over the square root of 1 minus u squared over c squared, which is the standard form of this Lorentz factor, the boost factor, gamma. Basically, this is the mathematics behind it, but if you imagine that you're moving through a subspace, typically if you have a observation platform here, you're going to have gyrons coming at you from all sides. It's a random gas, and the average speed hitting you will be c on all sides. But if you start to move through the gas in a certain direction, then this side they're coming in faster, and in this side they're coming in less fast. And when you average that up, it doesn't go to zero. It's actually a net increase of pressure as you're moving through, and that is the increase which corresponds to this boost factor. So your clocks are going to tick a little slower. Your meter sticks are going to be longer. Well, of course, in your own frame, a meter is always 1 meter, but longer than the one measured in this frame. And so once you have this Lorentz boost factor, you can derive the rest of relativity, and that's typically done in a freshman physics class, determining the energy, the kinetics required for using this change of frame. And this is a nice statistical way to derive the motion, the relativistic boost factor, based on a model of subspace that is very simple, just a Maxwellian gas. Of course, we're going to need more complex models to produce the other things that we're going to need to produce. For example, we're going to need to produce a metric tensor. We're going to need to produce electric fields, magnetic fields, and massive particles, such as the electron. So that's coming soon. But it's nice to have a background that we understand how our space-time is built from a very simple model of statistical model of subspace mechanics. See you next week.